Good morning, everyone. Hmm? আচ্ছা আমি দেখ So, good morning each and everyone. I hope you are enjoying this particular course on Laplace transform calculus and its application in differential equation. There was very few questions what I observed actually. The first thing is obvious question that why the Laplace transform I should study. What is the necessity of Laplace transform? So, and the Fourier transform of course, in general I should say that the integral calculus. Now, this integral calculus, that is Laplace transform and Fourier transform, which we have covered in this particular series, this is very useful for the problems which very frequently occurs in science and engineering. If you see, in science and engineering lot of problems are coming. I am talking about the Laplace transform. If I try to solve an ordinary differential equation using Laplace transform, then the advantage is that once I am using the Laplace transform, so automatically the Laplace using Laplace transform, the ordinary differential equation will be transformed into an equation of algebraic form, and we know that the solution of algebraic equation is very easy. So, effectively when I am using the Laplace transform to solve one ordinary differential equation, then it gives me or it transforms the ordinary differential equation into a algebraic equation, and the solution of algebraic equation is very easy. This is one part. Similarly, whenever I am trying to solve one partial differential equation using these transform techniques, they basically what they does, the number of independent variables it reduces by 1. That is, if I have 2 independent variable and 1 dependent variable in a partial differential equation, if I try to solve it using the transform technique, in that case the equation will be reduced to only 1 dependent variable and 1 unknown variable, independent variable, and again finding the solution of the independent variable will become easier for us. So, that is the basic motivation of learning the transform techniques. So, effectively this transform techniques is nothing but a tool using which we try to solve various kind of problems which occurs in different engineering and the science problems. This is one thing. Another thing is that some people was asking about the books on Laplace transform, and on this you can use any one of these two books. One book always you can use. Integral transforms, and their applications. This is one book. Another book you can use is that by Ian Snedden. So, as a reference book, if you wish, you can use any one of these two books. So, please note down these two books, Integral Transforms and their Applications by B. Daris and The Use of Integral Transform by Ian Snedden. I hope you have written these things. So, as and when required, please use these books. There was another question, I think, that is how to prove the proof of this theorem. The original problem was, what was the original theorem? If Laplace transform of the original, just 1 minute, let me just see. Okay. Just 1 second. So, just read down. If we restrict ourselves to a function f t, which is piecewise continuous in some finite interval where t lies between 0 to n and is of exponential order, some exponential order, then the inverse Laplace transform of f t, that is Laplace inverse of f s, this is equals f t. This is unique basically. So, in other sense, if you have a function f t which is piecewise continuous and it has the exponential of order alpha, then the inverse Laplace transform exists and it is unique. Actually, what happens, we have not given the proof for one reason. Your f t is Laplace inverse of f s. Once f t is Laplace inverse of f s, this actually we can write down in the integral form as 1 by twice pi I limit t approaches infinity gamma minus I t to gamma plus I t e power s t f s d s. And basically this is nothing but a complex integration, and I have to find out the value of this integration and I have to use the contour integration. The proof is very large because I have to evaluate this using contour integral, since it is a part of the complex analysis. So, those who are interested, they can go through the complete solution of this one, evaluation of this integral, and this produces a definite value. Once it is producing a definite value, that means the f t, that is capital F t, or this one is unique. And so, effectively if you see, this Laplace inverse of f s is nothing but this integral, which is a complex integral. Therefore, this complex integral we can use here. This complex integral we have to evaluate, and once you are evaluating the complex integral using the contour integration, we will find a definite and finite value. For this reason, we skipped this particular theorem, the proof of this theorem, because it is beyond of that scope, it takes lot of time over there. There was what happened this is fine. There was another question, I think, what was the motivation to start expressing any system as differential equation? This is basically what happens. Why any system, whenever you are talking about, suppose I want to travel or I am running. Once I am running, I started and I ended at particular one point. Now, I want to find out what is my velocity or how much I have covered, how much distance I have covered at what particular time and like that. So, basically the rate of change of a particular variable or value with respect to certain parameter, that is, it may be time, it may be any other thing, which is very easy to represent in terms of either differential equation or in terms of the ordinary differential equation or in terms of the partial differential equation. So, effectively whenever you are writing something like this, dy dx, this is equals to say 1. If you write down this thing, this means the rate of change of y with respect to x. So, any system, any physical system, if you think about, any physical system can be represented something like this way, either in terms of ordinary differential equation or in terms of partial differential equation. So, once I am representing this in terms of any kind of ordinary or partial differential equation, so automatically ultimately when I will solve this, I can obtain y as a function of some function of x. So, that if I supply some value of x, I will correspondingly obtain the value of y. That is the basic reason that when a system I am representing, it will involve some variable, I have to represent it in terms of some variables, where the variable nature of the variables will be, some will be dependent variables and some will be independent variables. Ultimately, what is your aim? Your aim will be to express the dependent variable in terms of the independent variables, so that once I can supply the value of the independent variables, I can obtain the value of the dependent variable. You can think it somewhere other way also, that if I have certain values, from there I want to predict what can be the possible value at particular point of time. So, to represent that thing, basically we are representing any system in terms of the integral in terms of the ordinary or partial differential equations, and then we try to solve this. This is the basic reason why we try to use or represent a system in terms of some equation. You may find sometimes we are representing it in terms of algebraic equation also, whenever you have done some numerical problems in your school level. When at your school level you are solving some problem, always you try to form some variables, something like this, say x1 plus x2 plus x3 equals say 15. I know say 3x1 plus 2x2, this equals 20. Like this way you have represented it in terms of algebraic equations whenever you are trying to solve some problems of your school level. Now, here also whenever I have a system, I will represent the system in terms of the differential equation. Depending upon the nature of the problem, the differential equation may become ordinary differential equation and it may become the partial differential equation, which we try to solve using these techniques whatever we are learning over here. So, these are the basic reason why you are using the particular equations. There was another question that is this subject only for postgraduate or also for BTech undergraduates to write the exam. Effectively, any student can write this particular exam, although this subject is coming under BTech courses, but at many places whenever there is a difficulty, there is a problem in mathematics, then people usually tells that please study this subject, because this Laplace transform and the Fourier transform or other transform not only applicable for the subject of undergraduate level, but also for the subject of postgraduate level. Therefore, anyone who is either from BTech or from postgraduate can write the exam and can get a certificate. I will encourage each and everyone to sit for the exam, because in that case what will happen, once you are getting a good grade, you will be confident that I have learned certain things and which will be useful for your career also afterwards. Any other questions was there? What is that?
Bessel function and Bessel equation.
Bessel.
Bessel function and Bessel equation.
What is the question? Where is it?
Slide number 157.
Slide number
157.
What is the question? Now, what they have asked? You have written assignment number 2, question number 4, I think. Just let me check, but I think that is not Bessel function.
No, Bessel to the expansion.
Acha, Bessel is the next one. Okay. Your FT, it is given that and of course, f of t plus 4, this is equals f t. So, I think the question was to find out what is the Laplace transform of this function f t. Since f t plus 4 equals f t, it is given already, which implies that f t is a periodic function. F t is periodic function with period 4. So, we know that if a function is there f t whose period is t, for that type of function Laplace transform of f t is equals to 1 by 1 minus e power minus s t into 0 to t e power minus s t into f t dt. So, Laplace transform of f t, where f t is a periodic function with period capital T, Laplace transform of f t, this actually we have discussed how this formula has come. So, 1 by e power 1 by 1 minus e power minus s t 0 to t e power minus s t f t dt, and for this case your t equals 4. So, therefore, the Laplace transform of the given function will become something like this. I hope you have noted this thing. So, once I am doing this, so Laplace transform of the given function f t, this will be equals to 1 by 1 minus e power minus 4 s 0 to 4 e power minus s t into f t dt. Now, your f t is 0 in 0 to when t lies between 0 to t and e power t when 2 to 4. So, therefore, this I can write down 1 by 1 minus e power minus 4 s into 0 to 2 e power minus s t into 0 dt plus 2 to 4 e power minus s t into e power t dt. So, that you have only the second integral, that is I can write down 1 minus e power minus 4 s into 2 to 4 e power minus s minus 1 e power minus s minus 1 into t dt. And if you evaluate this, this equals, you can write down 1 by 1 minus e power minus 4 s into e power minus s minus 1 into t by minus s minus 1. The integration will be from, limit will be from 2 to 4. So, I hope once you are putting it, these values, you can directly find out the values now, which becomes quite simple and quite obvious. And if I evaluate, I am directly writing the result, because you may have some more questions on other things. So, e power minus 2 s plus 2 into 1 minus e power minus 2 s plus 2 divided by s minus 1 into 1 minus e power minus 4 s. So, if you evaluate this integral, you will obtain this result, and I think the correct answer will be here. A correct answer will become C over here. So, effectively I have to know the Laplace transform of a periodic function to evaluate this one. If I know the Laplace transform of a periodic function, very easily I can find out the solution using this formula, that Laplace transform of a periodic function with period t is e power 1 by 1 minus e power minus t s 0 to t e power minus s t into f t dt. So, we have to evaluate this like this way. Just let me Someone has asked basically the Bessel function or Bessel equation. Effectively, Bessel function is a special type of differential equation of the form. I think I have also discussed this in the this one in our one.
159.62.
If you see, the Bessel function is nothing but the Bessel differential equation is of the form x square d2y dx square plus x dy dx plus x square minus n square into y equals 0. This is known as the Bessel differential equation, or sometimes we say that Bessel equation of order n. So, and Bessel equation or Bessel differential equation of order n is of the form x square d2y dx square plus x dy dx plus x square minus n square into y equals 0. Now, when n is not an integer or 0, the complete solution we can obtain as this: y equals a into j n x plus b into minus j n s into b j minus n x, where j n and j minus n are independent, and your j n we call it j n x is summation r equals 0 to infinity minus 1 to the power r factorial r into gamma n plus r plus 1 into x by 2 whole to the power n plus 2 r. This is beyond of scope how the proof is coming, but this is the solution of this Bessel equation, and which is actually the series is something like this: Bessel equation of the order n. And when n j n x is not an independent, then j minus n x equals minus 1 to the power n into j n x. And the complete solution we write it as a j n x plus b y to the power n x. So, that you can write down solution of Bessel equation of n equals 0 is this, that is solution whenever n is 0, your Bessel equation is will take the form d2y dx square plus 1 by x dy dx plus y equals 0, which is known as Bessel equation of for n equals 0. And the solution obviously comes as j0 x equals from the earlier one j n x we obtained. So, from that I can obtain the solution as 1 minus x square by 2 square plus x to the power 4 by 2 square into 4 square, like this way it will continue, where j0 x is called the Bessel function of 0th order. So, we gave some examples because more on Bessel function. Effectively, the Bessel function in itself takes 5 to 8 lectures minimum to cover how we can find out the solution. Since this particular topics is for finding the Laplace transform of different functions. So, we introduce the Bessel function, and then we are finding out the Laplace transform of various other functions like Laplace transform of j0t, Laplace transform of j0at, and we have given the proofs of those things. Then the solution we have done, I think you have understood the solution of this j0t, then Laplace transform of j0t, from there how it is coming, this one. So, those things I hope you have understood. So, more details, if you wish, we can post it separately on Bessel function, that how we can find out the solution of the Bessel function, that is second order Bessel function, whatever we have written, and how we obtain the solution of that differential equation. I will tell my students to post that solution, that from a second order equation, how I can obtain the actual solution of the differential equation, that we will post it to you. There was one query that you need some more examples on Fourier series. Effectively, in the upcoming assignments, more problems will be provided on Fourier series. So that you can practice more on the Fourier series. In the next assignment, they will provide you more problems on Fourier series. Where is the Fourier series?
Fourier series Fourier है अलग slide আছে
Acha, Fourier is
in this slide.
in this only the Laplace is there, because Laplace, up to Laplace it was covered. Okay. Okay. Any other thing they are asking? While watching the videos, how you are feeling, please write down to us, so that if you need any change, if you feel that we should provide you some more materials on certain topics, that always we can provide over here. We can do it. Please note this thing. Do you have the slide on Fourier series? So, effectively, if you see here, on Fourier series, we have done various properties, we have given the proofs. We have obtained A0, An and Bn. We have proved the convergence. Also, any function can be written in terms of the f(x) can be written in terms of A0 by 2 plus summation n equals 1 to infinity An cos n x plus summation n equals 1 to infinity Bn sin n x, where An, Bn are constants, provided if you see there is a constant on the function f(x) whenever you try to convert it in terms of Fourier series, that is f(x) is periodic, single valued and finite. F(x) can have a finite number of discontinuities in any interval, and f(x) has at most a finite number of maxima and minima. Then only we can evaluate it using this. So, that is if the conditions 1 to 3 are satisfied, then Fourier series of f x converges to small f x at all points of f x where f x is continuous. And of course, if the series converges, the average of left limit and right limit of f x at each point also will be equals. So, therefore, if the interval is alpha to alpha plus 2 pi, f x is defined by phi x in alpha to c, and from c to alpha it is phi x like this. So, then a n, a0, a n and b n also accordingly will be changing their limits, nothing else. And so, from there I think we have given some examples for evaluation of the Fourier series, Fourier sine, cosine series and the Fourier series also. So, if you see this problem, f x is a function which is a periodic function with period 2 pi, f x equals 0, where when x lies between minus pi to 0 and x from when x lies between 0 to pi. So, we have to first find out the Fourier series of f x, and then we have to find out the sum of this series 1 plus 1 by 3 square like this way, pi square by 8. So, your a0 is 1 by pi minus pi to pi f x dx, and you know what is f x. So, if you evaluate, you can obtain the result. Your a n is 1 by pi 0 to pi f x into cos n x dx. Your f x is, sorry, it is minus pi to 0, the value of the function is 0. So, it will become 1 by pi 0 to pi x cos n x dx. If you evaluate the integral, you will obtain this result. Similarly, you can obtain the b n x value. Your b n is 1 by pi minus pi to pi f x sin n x dx. Again, since minus pi to 0 function is 0, so it is 1 by pi 0 to pi x sin n x dx, and you have to simply evaluate the integral to obtain the result. So, once I have obtained a naught, a n, b n, I can write down my f x now in terms of the series like this way. And once I have done this, then for some value of x I can obtain the series, just like here at x equals 0, f 0 equals, whenever you are putting x equals 0. So, that sign terms will vanish and it will become f 0 equals pi by 4 minus this integral. So, that the value of the series 1 plus 1 by 3 square plus 1 by 5 square, this becomes equals pi square by 8. So, more examples or more questions will be given in the next assignment on Fourier series. If you have any difficulty, any problem on the Fourier series, you can ask us this one. Discrete Fourier transform, I think we have not done, or we have done it.
We have done finite Fourier transform.
Finite Fourier transform we have done, I think, but finite Fourier transform will come later, I think, in upcoming lectures. Finite Fourier transform definitely will come in the upcoming lectures, whatever you will listen. On that, the finite Fourier transform will be discussed and will be covered over there. What is the next one? Abel's integral equation.
Integral equation পরের লেকচারে ডিসকাস করা হবে।
When? $250.
40. 40.
$240.
40.
Find the solution of the integral equation.
Yes, sir.
there? Have we discussed?
No, sir, এখনো discuss করা হয়নি।
No, no. Abel integral equation, on which slide we have told them?
না স্যার, এবেল ইন্টিগ্রাল ওইভাবে পার্টিকুলার এবেল বা ভোল্টের আর কিছু করা হয়নি।
Afterwards, towards the end, we have done the integral, various kind of integral equations, how to find out the solution of various integral equations that we have covered towards the end. So, you have to just wait for that. Still, if you have any problem, then you can discuss, because just now you have started, I think, Fourier series. So, once we are doing the Fourier transform, during that time we will try to find out the solution of various types of integral equations, which will be covered in the later part of our subsequent lectures. So, please wait till that time, because we are going sequentially. In between we cannot discuss, because to find out the solution you need the concept of the Fourier transform also. So, unless we are covering the Fourier transform, we cannot go to the integral equations. Therefore, that will not be possible to explain to you at present, but in the subsequent, in the next or next to next meeting, if you have any query, please write to us and we will discuss that part if you face any problem any moment of time. Any other question is coming? If you have any other query, any problem, please write it now, so that we can address it immediately. Please do that thing. Anything else is there? Any problem on the assignment sheets which you face trouble or anything? কোন অ্যাসাইনমেন্ট শিটটা দিয়েছি? So, have you done the assignment, all problems on the second assignment?
Up to 4th it is published in the forum.
Up to 4th it is already published. So, have you faced any problem, anything while solving the problem? What is written? What is the question? Just wait, let's see what question you have, one of you has posted. why Fourier series have integral numbers of frequency if we talk about in forms of signals. Cannot we guess about what is this? Interharmonic form from decimal expansion of Fourier series. Actually, the question is not clear, but usually we take the integral form because it becomes easier to represent. If sometimes you have the decimal point or something like that way, in that case, using some multiplier, the decimal can always be converted into the integral part, the integer part, and then we can go for the solution also. Although it is not absolutely not clear that what was the question, but I guess what you want to say is that instead of integer, why not you are using the decimal expansion or something like that. But always decimal can be converted into the form of integral, and after that we can find out the solution over there, because the integral representation always it becomes easier for us, and any problem using some multiplier can be converted in terms of the integral form also. If possible, shortly talk about existence of Laplace transform.
15, slide 15, Laplace.
Slide
15, 1, 5.
Someone has asked to basically just recap the existence of Laplace transform. So, I will not write down, but I will see from here. If capital F t is a continuous function in every finite interval and is of exponential order a, whenever t approaches infinity, I hope you remember what is the function of exponential order a, then the Laplace transform of f t, which we say as small f s, exists for s greater than a. So, what is the proof? Proof is your f t is piecewise continuous in every interval and is of exponential order a. We know this thing. This has been given. So, suppose we are taking a variable t 0 which is greater than 0, then we know that the Laplace transform of f t or f s equals 0 to infinity e power minus s t into f t dt. This we can break it into two parts, 0 to t naught e power minus s t f t dt plus t naught to infinity e power minus s t into f t dt. Now, continuity of the f t in finite interval implies, because we have told that the function is piecewise continuous also. So, if the function is continuous in the interval 0 to t naught, then the first integrand, that is first integral 0 to t naught e power minus s t f t dt will exist. So, the basically the what I have to show in the other one, last slide if you see, we have told that it is your f s is 0 to infinity, we broken into two parts, 0 to t naught to infinity. Now, the function is piecewise continuous. So, if I assume that the function is continuous in the interval 0 to t naught, therefore, the function is in t naught, this particular integral value will exist. So, remaining part is we have to show what it is in the about the second integral. So, we have to show that t naught to infinity e power minus s t f t dt exist. Now, we know one thing, f t is of exponential order a. So, that means limit t approaches infinity e power minus a t into f t is finite. This we know. That is, given a number t naught, there may have a real number m such that e power minus a t f t is less than m. Basically, from the definition of exponential order, we are writing this, that absolute value of e power minus a t f t will be less than some real number m whenever t is greater than t naught. So, from f t, since f t is of exponential order, we can write down this, or from here absolute value of f t should be less than capital M into e power a t. So, if I take now the integral absolute value of the integral t naught to infinity e power minus s t f t, which is less than equals t naught to infinity, I can take the modulus inside and e power minus s t f t. This again e power minus s t, I can bring it outside, I can make it only modulus of f t, and modulus of f t is less than equals capital M into e power s t. So, that the integral is less than equals t naught to infinity e power minus s t m e power a t. M can come outside, t naught to infinity e power minus s minus a into t. And if you evaluate the integral, you are getting a finite value, that is m into e power minus s minus a into t naught by s minus a. So, effectively what you have done to find out the to give the proof of this uniqueness, I have taken the integral from 0 to infinity. From 0 to infinity, basically I am breaking into two parts, that is 0 to t naught and from t naught to infinity, that is t naught to infinity. I am writing 0 to t naught, since in function is continuous, piecewise continuous. So, in 0 to t naught the integral will exist and its value is finite. And for t naught to infinity, we have shown that the absolute value of t naught to infinity e power minus s t f t, which is equals m into e power minus s minus a t naught by s minus a. So, once I am showing this, therefore, can be made, if this value can be made as small as possible by choosing t naught sufficiently large. That is, if t naught approaches towards infinity, I can make this value closer to this. So, therefore, this t naught to infinity e power minus s t f t d t also will exist. So, that the inverse Laplace transform is existence of the, this completes the proof of the existence of Laplace transform. Now, someone has asked for proof of final value theorem. We have given it, I think, right?
Yes.
So, final value theorem says that let f t be continuous for all t greater than equals 0 and is of exponential order as t approaches infinity. And if f dash t is of class A we have defined the earlier, what happened? Just let me see. For limit t approaches infinity equals limit s approaches 0 s f s. So, for the proof, you know that Laplace transform of f dash t equals s f s minus f naught. This already we have proved earlier, I think. Then from here I can write down Laplace transform of f dash t is nothing but 0 to infinity e power minus s t f dash t into dt. So, this I am writing now. If you evaluate the integral, then limit s approaches 0 s f s minus f naught, that is, you are taking limit s approaches 0 on both sides of the given equation. And so, on the right hand side, limit s approaches 0 can be being inside, that is, limit s approaches 0 e power minus s t into f dash t, and if limit s approaches 0, that value is 1. So, that it is nothing but 0 to infinity f dash t dt. And if I evaluated this equals limit t approaches infinity f t. If I cancel both side f naught, then limit s approaches 0 s f s equals limit t approaches infinity f t. This completes the proof of the final value theorem. I think it is clear to you now, because you are starting with the integral. Basically, you are writing the Laplace transform of f dash t and then taking on both sides limit as s approaches 0. Another question you have given, you have guessed correctly. Actually, I want to apply Fourier series application to harmonic in power electronics. I just want help from you, that suppose f t equals 1 into t plus this. Can we write 0.3 t instead of 3 t? Can you just write or give me some hint how to expand this thing? Nishant, I think it would be better if you pose your question clearly, very clearly in the forum, because it is the time almost closing down. So, please post your this query along with exactly what problem you want to solve in the problem. We will definitely answer your query and clear your all the doubts, or if you have a example which you are not able to solve. It may happen that you have a question which you are not able to solve. You just write it on the forum. I will tell my students, they will consult me and I will give you the answer properly, so that your doubts are becoming clear, or even if you wish you can mail me. So, first write it to the forum that what is the exact question which you are not able to solve using the Fourier transform. So, please do it and we will answer you through the forum of your question. Ritesh, you could not register for exam due to null availability for exam city. Exam city is now the date is over, right? So, I think Ritesh, you just write to NPTEL IIT Madras posing your problem in which city you stay and where there is no center is available. Please write to them and tell them you are really interested to give the exam. I hope they will try to arrange something for you. Please write to NPTEL IIT Madras for this, because all the exams are conducted by them. The centers they are creating. So, please write to them, they will definitely address your issue. Any other thing? So, thank you very much. I hope if you have any problem, any query, any doubt, please write to the forum, so that everyone will know what is the problem, what is the difficulty, and we will try to address your problem. We will try to resolve your problem, we will try to solve your problem definitely. So, enjoy the lectures and I hope it will be really fruitful for you, all of us. So, I think next month we will meet again. Thank you very much.